So we have to, if we have to implement this algorithm, what would we need? Okay, recall the algorithm. In the algorithm, at any stage, we have some k subtrees. We have these k subtrees, and we want them to be ordered in decreasing frequencies, right? And then at each step, we pick the two subtrees which have the least frequencies, and we join them like this. Right? We create a new node, make them the left and right child, and basically that's it. Well, not entirely, because this subtree now we have to insert it in the right order of the remaining subtrees, right? We would want that at each step the subtrees are ordered in decreasing frequencies. Okay, so when we create a new subtree in the next step, we want to insert it in the right sorted order. Okay, but basically that is it. We need to repeatedly do this step, right, until we have just one tree. Okay, so that's the idea. Okay, so practically, how do we actually implement it? Okay, so what data structure would we need to do this? Well, we would of course need something like a binary tree to store whatever these left child, right child. We'll create a node which has some attributes. But other than that, we also require another data structure to implement this algorithm, right? Because we want to store the trees in the sorted order, and when we create a new subtree, right, we have to store it in the sorted order, and we'd like to get the minimum two, the trees with the minimum two frequencies. Okay, and we'd like to remove them from the list, and then we create a new subtree. We want to add it to the list in the right order. Okay, so what data structure would be appropriate for this? Well, I hope you see that what we really need here is a priority queue, right? It's a queue, but ordered on priorities, where the priorities are nothing but the frequencies here, right? It would be a min heap, right? We would want to extract from the heap the elements which have the minimum frequencies, right? So we would say extract min. Okay, for this, to get these two trees, we would call extract min on the heap 2 times, right? And then once we create this new subtree, we would just insert this subtree back into the min heap, right? Well, yeah. Uh, and well, we could use other priority queues also, but the one we know is a min heap. So that's why I'm saying that we'll use the binary min heap that we are familiar with. Okay. So, right. So let's write down the code for this. So the input to the problem is basically we have a list of symbols, right? This array or list of symbols S, and we have a list of corresponding frequencies, right? For each of the symbols, we have its corresponding frequency. Okay. So our code would maybe we'd say, give it a name. Our Huffman encoding would take as inputs these two lists, S and F, right? The symbol list and the frequency list. Okay. And maybe let's just use N as the length of this list. Either of them, they have the same length. And the first thing we'll do is we'll create these N leaves, right? We have to create these N leaf nodes. Okay, so now what will our node be? Our node is basically, it would be a class or a structure or whatever. So you would have the following attributes in the nodes. Okay, we would of course have a node represents a node in the binary tree. So we would of course have its left child and the right child. We would have these two attributes for the left child and the right child. What other attributes do you think we would need for the nodes? We would definitely need the frequency, to store the frequency of a node, right? Remember when we created a new node, for each node, we were storing the frequency, right? Which are the sum of the frequencies of its children for internal nodes. Okay, so that is an attribute we need. And we'll also, for the leaves, we would maybe want to store the symbol corresponding to the leaf. Okay, so for other nodes, it might be null, but for leaves, maybe we would like to store the symbol. Okay, so we have these 4 attributes. So we'll create these leaves first. Okay. So we'll say for I 1 to n, right? We'll say node equals new node. We are creating a new node, and let's give them, so the symbol here, the symbol attribute is basically SI, right? Okay, this is the symbol. Well, I could be 0 to n minus 1 if you like, but let's say they are indexed from 1. So symbol I and its corresponding frequency, right? The second attribute here is frequency of a node. So for a given index I, SI is the symbol and FI is the frequency, its corresponding frequency. Okay. Left child and right child for leaves are nil. So since these are leaves, we just initialize these to null. Okay. And maybe we'll just store them. So we'll store these in a list, right? Maybe initially the list of leaves is empty, and as and when I create a new leaf, I will just add it to the list. Okay, so I've created a new leaf and I append it to this list of leaves. Okay, why am I doing this? Now in the next step, what do we want? We have created our leaves, but now they are not sorted, right? We want them to be sorted, not entirely sorted, but we want them, as we discussed, we want them to be stored in a binary min heap. Okay, so let's create a binary min heap. So H would be our binary min heap, and one way is to start with an empty heap, and one by one we add the nodes, right? We're adding the nodes into the min heap, right? And we want to order the nodes based on their frequencies, right? So instead of adding nodes, inserting one by one, we have seen that the build heap operation is faster. Okay, so I'll say build heap. Okay, understanding that it is a min heap that we have build heap, and the set of elements in the heap are initially just these set of nodes we have created. Okay, just the leaves. Okay, so what we're saying is build a min heap, right? Build a min heap H, right? And nodes are ordered according to their frequencies. Okay. And yeah. Okay, so this is not automatic for you. You will have to do some work to get this to work. Like if you're coding in Python, you will have to do some work to, you'll have to you can define a compare operator, right? Which will let you compare two objects of a class. So if you have two nodes which belong to the node class, you can define a compare operator. You can override a compare operator that will tell you, which will let you compare two nodes, right? And inside that compare operator, you just based on the frequencies, you decide which node is greater or lesser. So if a node has a greater frequency, we'll say it's greater than a node which has a lower frequency. Okay, but for a pseudocode, let's assume that this automatically is happening. And now we'll basically run the main loop of the algorithm. So now again, we'll have for I 1, 2, we'll basically have n minus 1 iterations of this loop, right? In the final step, we'll just be left with this one tree. So, and in each step, what we are doing is, let's say, right. So let's say, maybe give it some name. X is the first thing. We'll extract the minimum element of the heap. So extract min from the heap. Okay. So what X would refer here is X is basically referring to the root node of this minimum, the subtree which has the min frequency, right? I hope you follow this. Okay, this is the subtree which has the minimum frequency in the heap, and X is basically a reference to the root of that subtree. Okay. Then once X, we have got X, then we need to find the second smallest, right? Which is now again got by the extract min, right? Because the second smallest will be the smallest once the first smallest has been removed. So we do 2 extract mins to get the 2 subtrees with the lowest frequencies. Okay. Now what do we need to do? Well, we need to create a new node, right? We need to create a new node which has the two children. Basically, this would be our X and this would be a Y, right? So we create a new node here. So let's say a new node, we just say node. Okay. So what are its attributes? What is the symbol? Where the symbol, internal nodes, it really doesn't matter. So we'll just say nil. But the frequencies, what is the frequency of this node? We see in that is just the sum of the frequency of this node and this node. Okay. So that is simply x dot frequency plus y dot frequency. Okay. And what is the left child of this new node that we are creating? The left child is simply X and the right child is simply Y. Okay, are we done? Anything else to do? Well, we have to, of course, insert back into the heap this new node that we have created, right? So insert this new node back into the heap. So it will put it in that sorted right place. Okay. And that is it in the loop. So this keeps repeating n minus 1 times, right? You extract the 2 mins, you create a new node where you join the 2 previous minimums like this, and then you put it back into the heap and repeat. Okay, so after these n minus 1 steps, in the end, you'll be left with just one element in your heap, right? That would be basically a pointer to the root of the optimal tree that you have constructed, right? So in the end, you could say just simply return the single node that is remaining in your tree, in your heap. So h dot extract min, right? So you return a pointer to the root element. Okay. So that is basically the implementation. How much time does this code take? Well, we have this loop here, which this loop here, which takes order of n time, right? You're creating n leaves. What about this step? Well, this step we have also seen in the previous course. I hope you remember. This can be done in linear time. Okay, so this is also order of n for binary heaps. Okay, and what about this loop here? This is running n times, well, n minus 1 times, but order of n times. And what about these steps? Right, we have seen that these steps takes order of log n time. Okay, the extract mins and the inserts, right? These can take order of log n time. So we have this running n minus 1 times n minus 1 times log n. So this entire loop takes order of n log n time. Okay, so the overall runtime of this algorithm, this code is, well, it depends on the data structure. When we are using these binary min heaps, we can do it in order of n log n time. Okay, so recall that our naive algorithm was simply exponential, and we are now with this Huffman's encoding algorithm, we can solve this problem really quickly in order of n log n time.